content is concerned, we will be having introduction, understanding of various terms used to define the turbulence. Anyone from audience, I would like to listen whether I am audible completely to the
Yes, sir.
audience.
Yes, sir. Yes, sir.
Fine.
Yes, sir. Audible.
So understanding of various terms used to define the turbulence, then computation of turbulence characteristics. What we will compute and how we will compute, that also we will do in terms of an exercise. I will give you data, 1 minute data of this uh, turbulence data or velocity measurement done by the acoustic Doppler velocity meter, and then very soon you would be able to compute these terminology. So moving ahead, as we know that turbulence or turbulent flow is a flow regime characterized by disordered and stochastic property changes. This includes low momentum diffusion, a feature of diffusion which is results of or which is resulting from mixing or mass transport without requiring bulk motion. So we know that particles are crossing path of each other, they are intermingled while they are flowing, and that is the onset of the turbulence, we can say. Convection, collective movement of groups or aggregates or molecules within fluids, and rapid variation of pressure and velocity. The turbulent flow, the nice example of turbulent flow, if you have traveled in Bombay suburban train, when a train stops and people comes out from the train and that into the train, that is the nice example of the turbulent flow, and a mass of people are coming out from the train, and there one is going in one side and other is going in other side, like that. So very rapid movement is there. Now when we in our undergraduate program, we generally concentrate over the turbulent flow in pipes. So here we do not talk anything throughout this 5 day, anything regarding turbulent flow in pipe. We would be concentrating, we would be measuring all these things for the turbulent flow in natural river or canal or laboratory flumes. So when we do the measurement in laboratory flume, we simulate that those things that they are happening in the natural rivers. So when we measure the turbulent flow in canal or in rivers, which we call it as open channel flow. What is the Reynolds number when flow will become turbulent in case of open channel flow? Anybody from audience?
Greater than 4,000, sir. Greater than
Greater than 4,000. Okay. Anybody else?
Greater than 4,000, sir.
Greater than 4,000. I'm asking
Sir,
about
1,000.
1,000. Okay.
1,000.
1,000. Any other answer?
Greater than 2,000.
Greater than 2,000. Exactly. So for open channel flow, which we are considering the flow in rivers or flow in artificial channel, which is flume, the Reynolds number, when it exceeds 2,000, flow becomes turbulent, and below 500 they treat as a laminar flow, and between 500 to 200 that says as a transition regime. So more often you will see that flow almost is happening in this turbulent regime, right? So turbulent processes in river strongly influences the velocity distribution, bed shear stress, energy losses, and sediment transport. So here our impact is also that how the turbulence is going to affect the sediment transport. As you know that when flow is taking place, the sediment particles are also getting lifted from the bed and get it transferred to the another position. As sir has spoken, bed load, transport, saltation load, or contact load. So whether really these movement, the movement of velocity fluctuations, are they responsible for the sediment movement? How they can be related, these phenomena can be related with the sediment movement. In coming lectures, our impact will also be there to to relate this flow field in the sense turbulence characteristic with the sediment movement. Because as you know that we can visualize the movement of sediment in a river. If you have a clean water and you are standing on the bank of the river and water is flowing, you can simply uh, witness the movement of sediment while standing on the side or on the bank of the river. So that movement really it is related with the turbulence characteristics or turbulent flow that we would like to enunciate in coming lectures through our experts from myself, and I will take quadrant analysis tomorrow, and we will also discuss one case study. Right? So a few pictures which are available, although taken from the net, you can see during the flood season or during this high discharge regime, how the flow becomes turbulent, and you can witness that eddies are forming, a lot of energy dissipation is taking place, everything is happening in case of turbulent flow. So understanding in practical aspect of the turbulence phenomena in open channel are widely. The advent of advanced technology like acoustic Doppler velocity meter enabled to measure the turbulent quantity accurately in both 2D and 3D open channel. Now let me ask you, when we have to get the velocity distribution, when we have to get the velocity distribution in case of turbulent flow, let me share another one. Is it visible?
Yes, sir.
Right. So when you have the velocity, sorry, like this velocity distribution, or you want to have the velocity distribution like this, when you have u value and y value on the y-axis, how we achieve this velocity distribution?
Sir, our screen share not visible.
So unable to see the presentation.
It is not there.
No, sir. No.
Wait. Why it is slow? Wait. Now it is there.
Yes, sir.
This one.
Yes, sir.
Yes, sir.
Now it's visible.
I think it is visible now.
Yes, sir.
Yes, fine. So when we are getting this, or when we are trying to get this velocity distribution, u versus y, or sorry, velocity at different along the depth. Suppose one flow is taking place in a flume where water is coming from here, and you are having some depth of water like this y. Right? So can anybody tell me how we will get this velocity distribution? This one from audience. Harsh is there. Nirav?
Sir, there is a device which is known as the current meter, so we can measure the velocity using current meter.
Okay. Current meter, exactly. Nirav? So how we will use this current meter? The procedure to get this velocity distribution?
Sir, current meter we use up to matlab ki for various depth to find the value of velocities,
Yes. So you
which
need
also
to say,
shows the variation in
yes, you need
velocities
to say
at
if this is the
different
bed,
depth.
yes, this is the bed level of channel which I have made here as a longitudinal section. So throughout this depth, we will insert the current meter at different location here, right? And then we will measure the velocity at these locations, and then you will plot these this velocity distribution, right?
Yes, sir.
Right. So which velocity we are measuring here?
Sir, average velocity. Average velocity.
Average velocity, exactly. Average velocity we are measuring, and again we are measuring only u, that is unidirectional velocity, and velocity in longitudinal direction. So when particle is moving from here, a particle is moving from here in this direction. So we assume that particle is moving in a straight line. So that's what we measure, the single dimensional velocity or unidirectional velocity, that is u. But truly speaking, the particle is moving like this in xy coordinate, and it do move like this in xz coordinate. Means it is moving up and down, although it is moving laterally and linearly also. Do you agree with this?
Yes, sir.
Right? Particle is not moving straight as a moving in xy coordinate. When I am making xy coordinate, that means if you consider there's a top, this is longitudinal, so particle is moving like this. If you consider as a top view plan, if you look from top, then again I make like this, so that is an xy. So x is here and y is here. So I mean to say, particle is moving in all three directions. It is not a straight line movement, but because of non-availability of instrument, or should I say, whatever is the available to us, we only consider that is single directional velocity, u velocity, right? And also we measure the velocity at a point for a certain duration. Now, truly speaking, the velocity distribution, if you measure this u, the velocity distribution is like this. It is not constant. We are taking this as a average. So if you consider this 1500 second time here and u on this x-axis, you can imagine that this velocity is continuously changing. If you trace a particle for this much second, 1500 second, then you would be able to know that the velocity is continuously moving in up and down direction. So my summation is that when we are going back on this again, do we need to measure this three velocity, all UVW? And definitely yes. Right? Deepak bhai?
Yes, sir.
Yes, sir.
So with the advent of, when I come back on this my previous presentation, let me share again that thing. I think it would be possible. Oh, sorry. It's not required. So I'm sorry for that. I have shared from beginning, but it should have been a current slide, right? So now this, with the advent of advanced techniques like acoustic Doppler velocity meter, which enabled us to measure the turbulent quantity or turbulence quantity accurately in both 2D and 3D open channel flow. Initially, there was advent of 2D measurement, like only we would have been able to measure u and v, but now with this ADV, it is possible to measure all three directional velocity UVW, which just we discussed, in x coordinate, y coordinate, as well as z coordinate. Right? And physical explanation and understanding of open channel turbulence are now being investigated quantitatively through many unknown features, which is still to be explored. And it is a topic of research. If you see, a lot of papers are upcoming since advent of ADV. Initially, how ADV is working, over that also people have written research paper. What is the phenomena of ADV, on which principle it is working, how it is measuring these velocity, everything it was written. Right? So this is just a view, although in the next lecture, Sudhanshu will explain all the things of basic principle of this ADV for you people. But to understand this contains three probes. You can see this three probes here, and this is one manufactured by this Sontech acoustic Doppler velocity meter, which measures the velocity in all three directions. You can see this, which is installed in a flume. This flume is there. We had one stand made for this acoustic Doppler velocity meter to be installed, and this, you can see this water is flowing here, and we are this cable is connected to a computer which is gathering the data. As the sir has spoken that 25 hertz or 40 hertz, like that. So now coming to the understanding of this characteristics of turbulence. So again, turbulence is one of the main controlling factors which is affecting the character and intensity of many river processes like erosion and sediment transport, flow resistance, bed morphology, and the platform of the natural channels. Now, sediment transport
Excuse me,
models.
sir.
Yes,
सर एक डाउट था सर.
yes, बोलिए. Yes, definitely.
सर आपने जो एडीवी जो एक्सप्लेन किया है, तो
Yes,
इसमें मतलब कि we can measure the velocity component also, or we can measure just the turbulence.
we can measure the velocity components in all three directions. That is also, I'm coming on that thing only. And from the velocity component, we would be calculating the turbulence characteristics in terms of various terminology.
Okay, sir. Okay.
That will give only velocity. But it will give the ample data which we have to analyze, and that we have to go forward for next calculations, right? So the sediment transport models applicable to different bed surface geometry can be made more accurate and predictive if we can understand turbulence characteristic or turbulent characteristics. Now, what reasons behind to study these characteristics? So again, this is one of the main factors which is affecting the river processes such as erosion and sediment transport, flow resistance. Although we will relate all this thing in coming lectures, just I am giving a preamble here that this turbulence characteristics is also related to the erosion sediment transport. But as we passes on in the various lectures, these things would be very much clear to you. Then turbulent flow is accompanied by fluctuations, formation of eddies, as we are knowing this at macro as well as micro and as well as macro level. And we of course knows it that is on the high Reynolds number. And truly speaking, if you perform any experiment, when I go back on this figure, when the water is flowing here, and if you measure the Reynolds number as far as open channel flow is concerned, you every time will get more than 2000. So in all cases, whenever you perform the experiments, the flow is always turbulent. So when flow is turbulent, these characteristics which we are going to discuss, they all are happening, and we are if we are having such instrument like acoustic Doppler velocity meter, then probably we are able to measure it. Otherwise, we will measure single line velocity. Just we have discussed current meter. Current meter is there, but even current meter is not there. You can use pitot tube. Pitot tube is also there, which is used to measure the velocity at different.
Piezometric head.
Yes.
Yeah, piezometric head. Yes, without you.
Yes, pitot tube we insert in the flow, and we calculate the difference in manometer tube, and by that formula under root of 2gh you calculate the velocity. We Torricelli formula that you use. So pitot tube is also one accessory which is available in most of the labs, and which can be used to measure the unidirectional velocity or single line velocity. So that's what we would like to study, this turbulence characteristics. Now explaining these quantities mathematically are like challenging task. However, some semi-theoretical relationship exists to understand the turbulence characteristics in open. A researcher have also worked on uniform sediment as well as on the non-uniform sediment, and quantified the characteristics of turbulence on such bed. This present whatever at present moment, the study related to quantification of turbulence characteristics over non-uniform sediment beds are scarce in the literature. If you see particles which are of uniform size, they are laid on the sediment bed, and accordingly this one all characteristics are calculated. But even though the particles which are having non-uniform gradation, two different sizes or various sizes are available on the bed, we can also calculate this turbulence characteristics. Now, sediment in nature are invariably non-uniform, as we know, and the characteristics of turbulence signatures on the flow over such sediment bed, they undertake foregoing experimental investigation. Now, we know that flow at large Reynolds number ceases to be laminar and it becomes turbulent. In each point of flow, the instantaneous velocity. Now, I use this word instantaneous velocity, UVW, is subjected to the variation in direction and intensity. When I say the instantaneous velocity, what we understand by this word?
The velocity at that point.
At that point, okay? See, when we have this instantaneous velocity, so what sir was telling that 25 hertz. So 1 second it measures 25 observations of velocity. Velocity means u, v, and w. So if you take the reading for 1 minute, how many observation you will get?
25 into 60.
Oh, yeah, that's what I want.
1500.
1500.
1500.
Right? So 1500 observations at a particular point. Suppose if you have a channel uh, which is having water up to this depth, say 15 centimeter depth is there, which is flowing in open channel. Now you have inserted your ADV like this, three props, right, at a particular point. Say this is 10 centimeter below the water surface, right? 10 centimeter below the water surface. You inserted ADV, your instrument. At this particular point, if you keep that for 1 minute, if you keep that ADV for 1 minute at this particular point with this frequency 25 hertz, it will gather 1500 readings of U, V, and W. Is this clear?
Yes, sir.
Yes.
Yes, sir.
Everybody, because see, this is very important to understand how much readings we are getting and how we are using those readings to our calculation. So it is necessary to understand. So accordingly, one few of you have raised, can we go for the 40 hertz? No problem in going in 40 hertz, but in 1 second it will record 40 readings. So if you go for 1 minute, you will have to have 2400 readings. You will gather 2400 if you go reading for 1 minute. So when we perform the experiment and we want to plot the velocity distribution, in that case we insert our acoustic Doppler velocity meter throughout the depth. We keep it here, we keep it here, we keep it here, we keep it here, like that at different positions, and maybe for more than 3 minutes. So when you keep this at more than 3 minutes, you have to get around 4500 readings, right? So if I go back again on that one, see, we can see this from current slide. Just I'll go. I am showing you this one. See this one. So if you see this, this is the reading from one of the computer screen where the data are recorded in terms of velocity measurement. You can see this U is there here, and this reading is taken from 0 to 100 seconds. Time is written in seconds. So hardly more than 1 minute, 1 minute and 40 seconds we are recording. So this could be done for 3 minutes also. So you will get like 180 seconds here. And for those 180 seconds, you will get 4500 reading of this U, like this fluctuation from year to year. V, similarly, that is the lateral velocity, right? And W, that is the vertical velocity, either vertically up or vertically down, right? So if you see, generally this linear component that is having most dominant value. When I will give you the data for U, V, W component, all three, you will also see that U component has most dominant value compared to the V and W. So we understand that because water is flowing in X direction, so naturally the velocity should be largest in X direction compared to the Y and Z direction. But although those values are also available, means we cannot neglect those values. Right? So this one, now coming back over this. So flow at large Reynolds number ceases to be laminar and it becomes turbulent. And each point of flow, the instantaneous velocity UVW is subjected to the variation in direction and as well as in intensity. So that we can see from this one. Now, when we have to express this thing, the variation around the mean velocity, how we can express U at any time. Now, this is instantaneous velocity. When I was spoken or I was asking about the instantaneous velocity is the velocity at a particular time. So, at a particular time, this would be the average plus U prime. Similarly, V average plus V prime, W average plus W prime or W dash, whatever you call. So, the fluctuation component that U prime, V prime, W prime are by the definition they are weak compared to the respective value of U, V, W. Now, if I go back on this photos again, now can you see U prime and U both here? Deepak bhai? Audience?
Yes,
Chittaranjan?
sir.
Yes, sir. There is a difference.
Yes, sir. Yes, sir.
Yes, can we see this U prime and U bar or U average, whatever, in this figure?
Sir, it's in the green.
Dotted green line. Dotted green line, sir. You have it.
Dotted green line is U prime and dotted green line is U prime. And then what about U bar?
You have the dotted green line. U bar.
U bar. Okay. Sanman is saying dotted green line is U bar, and then what is U prime? Let us go back to the definition again. Sorry. I'm going back. Oh. Have to go back. This one. So let us go to the definition again. U is U prime, U bar plus U prime, V bar plus U prime. Right. Now again I am going to that figure. So anybody in this figure, can we get Naved? Naved is there. Yashwant is also there. Dr. Umesh Singh.
It is instantaneous.
Yes, Naved is saying. Yes, please.
So that is instantaneous velocity.
Instantaneous velocity, Nirav. Okay. But what I want to know is at any point are we getting this U and U prime? So my submission is that at any time when you take from 0 to 100 seconds, 90 seconds suppose I want to get. So this green line is U prime, sorry, U bar, and above this fluctuation, that is the fluctuation in velocity component, that is our U prime.
U
So
prime.
that will make U equals to U plus U prime. U bar plus U prime. And again, to be very correct, it would be plus minus. When I
Yes, sir.
Arithmetic. Plus and minus both. It could have a for a particular instance, it would be plus or minus.
yes. So when I need to write this expression, this would be U bar plus minus U prime rather. It cannot be only plus, as witnessed from the figure, or you can see from the figure. So v bar plus minus v prime, w bar plus minus w prime. So accordingly, at any point instantaneous velocity, you can see the dotted line is showing over bar, that is the average velocity, which we calculate, either you calculate from Pitot tube or you calculate from current meter. These velocity we are getting using this apparatus. But in case of this ADV, we are getting the continuous fluctuation up to, as I have spoken, up to 1500 readings or 4500 readings. You will continuously get these values. So you will get these values, and from that you will compute the average velocity by taking time average of these three. Right? So this, when we want to define this intensity of turbulence or turbulence intensity, temporal mean value of the velocity fluctuation are zero by definition. How we can say this?
Sir, because the positive and the negative will become equal, so we can say that u dash is equals to 0.
You mean to say whatever fluctuation above this dotted line and whatever value below
Yes,
the
sir.
dotted line should be almost equal.
Yes, sir.
Right?
Yes, sir.
Meera barabar છે ને? Naval is also there. Naval, are you listening?
Yes, sir.
Right? So could
Yes,
you
yes.
enunciate this, how this u prime is 0? This value from this figure.
Yes, sir. Middle dotted line explain the variation between over and maximum and minimum event.
Yes. Yes. So these values above the dotted line and below the dotted line, they would all be almost equal. So by definition, we can say u dash or u prime would be 0, but this is not, however, the case for mean quadratic value. When you take the mean quadratic value, means root mean square value, you keep on going squaring
Yes,
this
yes.
value u prime. In that case, they will not
Yes.
be 0.
Okay.
If you
Okay,
calculate
sir.
u prime and make it a square, algebraic sum would be 0. But if you take root mean square value, that value will not come 0. बराबर છે ને? So let me go back.
Yes, sir.
Like if you have sorry, pen has gone. Oh, sorry, it could be. If you have u plus minus u bar plus minus u prime equals to your instantaneous velocity. This is instantaneous velocity. So these value, like suppose minus 5, 4, minus 3, 2, minus 6, like that. These are suppose plus minus value. So algebraically, if you go on summing, probably they are coming out to be 0, which we would like to explain, or whatever we have been understanding. But if you are going on squaring this, and then you take this root mean square value, would you find this value as a 0?
No, sir.
No, sir. No.
No, sir.
No,
It
sir.
will not be 0. So this is what the fluctuations in the velocity component. This u prime is the fluctuation in the velocity component, and that is defining your turbulence. And truly it should be, suppose if you are having your जैसे आपका heart का rate होता है ना, so when we have cardiogram, so we get like this. और अगर ये ऐसा आ जाए तो क्या होता है सलमान?
Death, sir, death.
Die. So that means God also wants you to be turbulent. You cannot be laminar, you cannot be smooth. बराबर है ना? दीपक
Yes,
भाई?
sir.
Yes, sir.
So when we do our cardiogram and we get like this fluctuations, so from mean line, whatever from mean line this is going, these all are turbulence parameter, that fluctuation. So that's what we are going to measure in our study, in our turbulence study by ADB. So this you can correlate from this cardiogram. So I mean to say, if you take this algebraically, then you will get zero. So there is no turbulence, but it is not like that. You go on squaring it and take the root mean square value, probably you will get definite value of turbulence. So going back on this our presentation. Right, so this is not, however, the case for mean quadratic value. Now, defining this turbulence intensity, just we have spoken or I have spoken, the fluctuating turbulence is mainly represented by its intensity. Now, quickly, within 5 to 10 minutes, we will finish and then we will do some exercise for this calculation. So, turbulence intensity in the longitudinal or flow direction, we can define as root mean square of u prime. So, you calculate u prime, square it, and then take root, you will get the turbulence intensity in u direction or x direction. Similarly, you will do for v, and similarly you will do for w. Right? The ratio of root mean square velocity and the friction velocity is used to define the intensity of turbulence. Generally, when we plot in non-dimensional form. So we centimeter per second divided by centimeter per second. This is a non-dimensional form. So u prime square divided by u star. We define u star as a friction velocity or shear velocity. So that shear velocity, if you look into the literature, if anybody can say the expression for shear velocity. Anybody? They will? Hers?
Square root of shear stress divided by density.
Square root of shear. I want an expression form. Probably the definition may be.
Sir, rho into v square, where v star is equals to shear velocity.
Yes, rho into,
Okay.
or you can say u equal to u star under root f by 8. That is one
Yes,
also
yes,
method.
yes, sir.
From that you can determine
Yes,
u star, that is shear velocity. So the same thing, the friction
yes, sir.
velocity or shear velocity we use to define this. So this would be the function of z. That means in terms of depth. Here we are taking in terms of depth. Right? Similarly, this w root mean square of w component will also be the function of z. Right? So that is turbulence intensity. Now, in case of uniform flow, I'll go on doing this big one. So vertical distribution of turbulence intensity in case of uniform flow, if you see the u prime root mean square of u prime to u star, it is almost uniform. Means although it is maximum at the bed, near the bed, and if you move towards the top, the value is reducing. That is in case of the uniform flow. For the both, like w component and u component, now you can see the value of u component is larger here, 2. It is starting from 2, wherein the value of component w is starting from 1. So it is going up to 0.5 or something like that. From 2, it is going up to the 1. So that is in case of uniform flow. Contrary to it, if you draw the same variation along the vertical or along the depth of the channel, you will see that the distribution is somewhat like this. So this is in case of non-uniform flow. When I have spoken uniform flow, the flow depth is constant. The depth of flow is not changing in previous case. So almost same in a channel, but if it is changing, the variation is like this. We'll discuss more in coming lecture, but just for information, this is there. So that is vertical distribution of turbulence intensity in case of non-uniform flow. Now, in case of accelerating flow and decelerating flow, where we consider the unsteady part, although in more cases we keep discharge constant. Generally, discharge constant is there. But if your flow is accelerating or decelerating, like unsteady flow, then turbulence intensity is smaller than that of uniform flow. The maximum value is at bed and diminishes towards the water surface. So that means in case of accelerating flow, turbulence is suppressed. If you are increasing the discharge continuously, the turbulence is suppressing. In another way, you can say the energy is getting dissipated. That's what the turbulence is suppressing. But in case of decelerating flow, the turbulence intensity is larger than that of uniform flow. The maximum value is above the bed and diminishes the towards the water surface. When I say above the bed, I mean to say the river bed or channel bed. So as you know, the velocity distribution starts from channel bed and goes up to the top. So accordingly, the variation would be plotted. In decelerating flow, the turbulence is enhanced. So that is also the comparison between accelerating and decelerating flow. Right. Now, another terminology we can calculate turbulent kinetic energy. So this also you need to calculate in your exercise. This turbulent kinetic energy is the mean kinetic energy per unit mass associated with eddies in turbulent flow. So if you have more kinetic energy, you can say the eddies, development of eddies are large. If you have less turbulent kinetic energy, the development of eddies is less. So that would be computed using this expression, that is half of this u prime square mean and v prime square mean over bar and w prime square over bar. Wherein this u prime square you can understand, this is ui minus u bar square divided by total number of observations. Suppose you have 1000 observations. So what you will calculate? First you will calculate u mean, and then from each component, that is ui, you subtract that one and calculate a square and going on averaging it 1 by n, that you will get u bar square. Is this clear?
Yes, sir. Clear.
Or shall I go for one? Let me go and explain you. Just wait a minute. See, if data like this, you have u maybe 178 minus 50. That is our instantaneous velocity, right? And minus 40, then 60, 63, likewise. So what you will do? You have to calculate u bar. That is the average value. Right? And then if you want to calculate this u prime, so u prime is nothing else, that is ui minus u bar, right? And squaring this, you will get this one, and average, that is 1 by n. So say this value is, let us take 54 for example. So what you will do? ui minus u bar, so that is 100 minus 54, 78 minus 54, minus 50 minus 54, minus 40 minus 54, likewise. And then squaring it, you will get u prime square and over bar, that is 1 by n. So whatever 1, 2, 3, 4, 5, 6, that is 1 by 6 of this value. This value, one value you will get. Similarly, you will get v prime square over bar, w prime square over bar, and half of that, this will give you turbulent kinetic energy. Did you get this, every participant?
Yes, sir.
It is a simple arithmetic calculation.
Yes, sir.
Right?
Hello. Yes, sir.
Sir, I have one question at this
Yes,
point.
please.
Can I ask?
Yeah, definitely.
Uh, Sir, while taking the observations through ADV,
Yes.
so we observe some spikes in the data. So are these fluctuations or spikes are same thing, or these two are different?
Those spikes are actually the irregular behavior of the instrument. That is not same thing.
Okay.
These are the what we can say the fluctuation in the velocity component, but those spike, that is the irregular behavior of the instrument. That's what we have to remove those spike, or we have to omit those data in our calculation. You apply certain filters, or you go on removing those spike by signal to noise ratio, or some methodologies are also available to remove those spike. So that is not this thing.
Okay. Sir, if you can please explain the spiking, because I am facing some difficulty while the spiking the data. So if you can explain it, it will be very helpful for me.
Definitely, if we will get time, then we would like to cover that spike portion also, how to remove those spikes. That also we will try.
Okay. Okay. Thank you, sir. Thank
So while this process, you would be calculating this turbulent kinetic energy. Although you will do for a single exercise. Suppose I'll give you 1500 data, which we can also see. This screen is visible. Let me see this is what you will have to do. This is the instantaneous velocity data, which is given for particular location at 2 meter, or sorry, 2 centimeter below the water surface. The data have been collected from ADV. Now you can see this velocity component u, instantaneous velocity component. It is starting from 104 and going up to this value, like this, up to 1500 data I have taken for your exercise. Then V component is there. You can see this is very less compared to the U, 24, 12, 3, -6, like that. And W component, that is a vertical component, up and down. So this 5.2, 26.21, -4.8, and so on. This total, you can see this is 1500 data is available. So what you need to do, you have to calculate this turbulence intensity in all three directions, turbulent kinetic energy, and Reynolds stress. That also we would like to just discuss. So escaping this, we'll go back to this one here from current slides. Okay, so this turbulent kinetic energy you would be able to calculate while you and it is a Excel calculation, so hardly it will take 5 minutes for your computation. It will not take more than 5 minutes. So u prime square, v prime square, w prime square you will calculate, and then you will get turbulent kinetic energy. And using this, you will also be getting this turbulence intensity, which is was the root mean square of u prime over bar. So is this clear? Neville, Salman, you would be able to
Yes,
calculate?
sir. Yes, sir.
Right?
Yes, sir. Yes, sir.
Then turbulence diffusion, we are not taking much time on this diffusion, although longitudinal turbulent diffusion we can calculate using this expression, or vertical turbulent diffusion also we can calculate using this expression. Now, most importantly, the quantity which we need to calculate is Reynolds shear stress. For a homogeneous fluid and incompressible flow, the flow velocities are split into a mean part and a fluctuating part using Reynolds decomposition. So this shear stress, see, we have calculated the intensity part, we have calculated the kinetic energy one. We can calculate the Reynolds shear stress also from the given data or from the observed data, which would be like expressed as minus of rho u prime w prime over bar. So you will calculate this u prime w prime and multiplying it with this density of fluid. Now this, how you will calculate this u prime w prime over bar. This is u instantaneous velocity minus u average, w instantaneous velocity minus w average. To take the mean of that, this value would be there, and that would be at all points. These value would be at all points. Then taking the averaging, you will get this value, multiplying by rho. How this is a stress? Can anybody explain me? Rho u prime w prime. I usually know the force upon area, that is Newton
Sir,
per
from
meter.
the formula, I can explain, sir, since V is equal to under root tau by rho.
V equal to under root tau by rho. From the formula that comes from here. Okay, but if I go with the basic thing, let me go back on the presentation again. Suppose, let me explain here. Sorry, let me take here tau minus rho u minus, just omit minus u prime w prime. So I go from the basic, the unit of this density in SI unit kg per meter cube, meter per second, and meter per second. So that is kg meter square into meter per second square. Is it correct?
Yes, sir.
So this is kg force, kg into acceleration, kg into acceleration divided by meter square, and it would be per meter square. So that is also correct, that under root of tau upon rho equals to u. So that will give you the probably shear stress. But when we multiply this quantity, the fluctuations in u, fluctuations in w, and multiply it with mass density, you will get the stress. So that is the bed shear stress or Reynolds shear stress, and it would be again different if it is channel bed here. So this is channel bed, and your water is flowing up to this depth, say y depth. So when you calculate these component at different elevations, all these elevations from say this is 15 centimeter, and every 1 centimeter you are calculating these observations or measuring this value, and then you will be able to calculate this shear stress at different locations, starting from bed to the top surface. Right? So this would be the Reynolds shear stress, which we will calculate in all three directions. This is tau. The major component is rho u prime w prime, but similarly other two component will also be there: rho u prime v prime over bar, rho v prime w prime over bar. All remaining two component will also be there, but if you calculate, you will find that those two components are very feeble in nature, very less effective in nature. So we are just omitting that, or they are not in fact influencing your flow phenomena. So in that case, this is the only quantity we would be taking as a Reynolds shear stress. Right? So I hope that this is the variation. Now, if you see the vertical distribution of Reynolds stress in case of uniform flow, it is more or less again a linear line, you can say, starting from bed at some value, and it is going to reduce at the top surface. But if you see in case of non-uniform flow, the variation would be different. It will not be same. This is again from one of the experimental data, but that is varying in this form, right? And again, in case of accelerating flow, the distribution of Reynolds stress is concave, and accelerating flow, the Reynolds stresses diminishes, wherein in case of decelerating flow, the Reynolds stresses increases. Right? So consequently, the energy dissipation, namely the head losses, is larger in decelerating flow than the accelerating flow because of these values. Right? So I hope that is the end of this today's presentation. 1 hour I would like to take, because since beginning it should not be heavy dose to you. But in the 15-minute duration, what I will ask Sudhanshu to share this Excel sheet. Sudhanshu, are you there?
Yes, sir. I have already shared.
Okay. So how they will calculate, and where they will submit it?
I
They
will
will have
I
they
will
will have
create
to
a
submit.
link for that, sir.
Okay. So I would say to all participants, I think it will not be a difficult task. You calculate this turbulence intensity in all three directions, and then turbulent kinetic energy and Reynolds stress. This would be the 2 days task, and it will give you the insight how these value when see I have shown you the plots आपने देखे हैं, they are looking very good. तो वो कैसे आते हैं, at least you can understand this. Dr. Singh is there,
Hello.
Neerav is there, Deepak, it is okay?
Yes.
Excuse me, sir.
Yes, sir. Yes, sir. The session was quite good.
Right. So I insist that, or I submit that everybody will do this calculation in the coming 15 minutes, and you will check your answer with yourself from other participants. I have not calculated it. I am just giving you the data. This data as observed. So once 2 or 3 people will get the same answer for the turbulence intensity and turbulent kinetic energy, that would be treated as correct.
Excuse me, sir. Hello.
Yes, please.
So in the data, I can see some negative values
Yeah.
for V. So what is the significance of this negative value? I think this data is from ADB. Is it?
Yeah, that is from ADV.
Okay. Then what is the physical significance of this negative?
That is the fluctuation which is happening in below the mean value. So that is negative value. When it is going above the mean value, it is positive value. Just wait a minute.
Excuse me, sir. Which quantity
Yes.
has to calculate? Which quantities has to be calculated, sir? एक बार आप repeat कर दीजिए. TE, sir. एक तो TKE है, sir. Turbulent kinetic energy. Second one is.
See, madam, can you see this figure on your screen?
Yes.
So from the mean value, see, this is the dotted line, which is the mean value. You will have all instantaneous. These are the values. So these instantaneous values are recorded as green line is moving. So this green line is moving, the V value is recorded. This orange line is moving, U value is recorded like that. But incidentally, in this case, the U velocity does not have any negative component because it is observed at near to the top surface of water. But had it been near the bed surface, you could have found U value also as a negative one.
Okay.
Right. So V is there, W is there. So accordingly, you need to calculate. Now, Deepak was saying exactly what to calculate. Is it?
Yeah. Is this the raw data or?
Yes, it is observed data from ADV.
Raw data itself.
Yeah.
Okay.
Observed data. Observed data. It has been observed for 3 minute duration. I have curtailed for 1 minute. Only 1500 observations are there for at 25 hertz frequency.
Okay.
So this 1500 1 minute data I am giving to you. Now, what to calculate is turbulence intensity. You need to calculate turbulent kinetic energy and Reynolds stress. That is only rho U prime W prime. So when I am showing back this one, see turbulence intensity in U direction, root mean square, U prime square over bar and square root. You will calculate this, and how you will calculate this from here. This one. So I keep this open, and you would be able to calculate U prime square over bar, V prime square over bar, W prime square over bar, and then you need to calculate kinetic energy, and at same time you do square root of this only, you will get the turbulence intensity.
Okay, sir. Okay, thank you.
Right. So this 3 value, and then Reynolds stress, that is there all. So just I keep this open, you can see, and if you need any help, we are there. Myself and Sudhanshu is available. We would be able to see. एक मिनट थोड़ा सा, mute. Yes, participant, did you get anything?
Yes, sir.
Laxman is there?
Yes, sir.
Are you doing this? Can you get?
Yes, yes, sir. I'm doing. Sir.
Okay. Salman? Samnan,
Yes, sir.
is it possible to
Hello,
do?
sir.
Yes,
Yes,
yes.
sir. Yes, sir. Possible.
You will do in Excel
I'm
only,
ready.
yeah? Just dragging it and doing it.
Yes, sir.
Right? Okay, fine.
Yes, sir. I will. Yes.
Yes, dear participants, any difficulty in calculation? Roshan,
Sir,
are you doing?
yes, doing, sir.
Okay, fine.
सर सर वी है ना सर
Yes, yes, बोलिए.
सर वी बार का एवरेज है ना वी बार जो है ना सर वो नेगेटिव में आ रहा है तो चलेगा ना
V bar average is negative.
वी बार यस minus 1.87 something.
Is it like this? Actually, I have taken few data. That's what. Maybe it come. Actually, data are of around 4,500. Out of that, I have taken 500. Let me check. Also doing it. Average. We cannot do anything. If it is coming average, then fine, no problem. How much it is? Yes, minus 3.75. Hanuman?
Minus 1.878.
1.87, yeah.
Minus.
Fine. Yes, yes, correct. No problem.
Hello, sir.
Yes.
Sir, completed, sir.
Okay, fine. So can you give me the answers?
Sure, sir.
Fine. Or you can post it in chat box if possible.
Yes, sir. I will message in the chat box, sir.
Pankaj is saying please share PPT in group for solving Excel sheet data. Okay, fine.
Sir, I got.
Yes, Nirav.
Yes, sir. I'll share my screen.
497 is what value?
Yes, it is the total energy. Share desktop.
Just share your screen so that we can discuss. Okay. Oh, that's gone.
Should I have dropped my answer in the chat box, sir?
Yes, turbine kinetic energy is 451. I think it is some larger value. Could not be. And shear stress, 16748. This much. There should be some calculation mistake, as I hope. Yes, Neerav is sharing something. U bar is this one, B bar is this one, W, and U minus U bar square, and then so just go at the bottom cell, Neerav, for 413 के bottom में जाइए. Neerav, can you hear me?
Yes, sir. Yes, sir.
Just go to the bottom of this cell where my arrow is there. 413.
Okay, just 413. 413.
Yes.
Okay, sir. It is that cell number, sir. 413.
Yeah, value, top value, 413. Okay, J column, J column.
Column, sir. खबर नहीं पड़ा सर. J. Okay, sir. J. Yes, sir. J.
Bottom.
Yes. This is what.
Yes, sir. TKE value is lower, sir. Sir, there was a problem in formula, sir.
That's what I was expecting. Similarly, maybe the shear stress, it could not be this much value. I hope that.
Yes, sir.
You have taken
We
this,
might have got the formula wrong in the Excel
U
programming.
minus U prime, so that is okay. 20, 26, 24 minus S, that's also okay. 5 minus 30 square. So you do it squaring and then taking divide by 1500, summing and divide by 1500, that would be U prime square over bar, right? And then square root.
Yes, sir. Sir, that is what I think I did.
Just share your screen. Yes.
This is the U bar. Yes, sir. I will share.
Just
Sir,
go
first
down.
is the U bar. The
Yes.
sum total of all these divided by 15.
Okay.
And then U
just
bar
I'm interested
for
in J column. That is correct. That I can see. J column at the end.
Okay, and then yes, sir. This is the last thing that I found.
497. Okay.
Yes,
What
sir.
is this? Is this turbulent kinetic energy?
Yes, sir. Turbulent kinetic energy.
Yes, sir. 497, sir. So my answer is also 497.
Also. So that means that is correct. Okay. And then what about shear stress?
We can see the shear stress, sir. No, I have not found it yet. Let me, sir. I'll find it, sir.
Okay. So to all participants, these value 497 is turbulent kinetic energy. That is correct. But you need to calculate the turbulence intensity also. That square root of that value. Just share your screen again.
Yes, sir.
So these values 689, 213 and 92. That is U prime square over bar, right? This is V prime square over bar, and W prime square over bar. Now we need to calculate turbulence intensity. So its root mean square. That is the square of this, square root of this. So 689 around 25, near about 25 you will get that value. Then 213 near about 10, 12 or so. You can do Neerav here to get the square root of this number, all three. So this is turbulence intensity, 26.
Yes, sir,
right? Deepak?
Sir, for Reynolds shear stress, rho की value 1000 होगी ना sir? The rho value
Yes,
of
rho is 1000. Yes, that is 1000.
No.
Sir, then my answer is correct. Sir. 16748.
I was looking only U prime W prime. That's what I was saying. it should be very less, but you have multiplied it by rho also. So generally we do
Sir,
not.
U prime W prime is minus 16.748.
Yeah, so that's what you multiply 1000, so it becomes 16748.
Yes, sir.
Yeah, fine. So I was looking on that value 16.74, because when we plot, we generally plot only U prime W prime. We do not take a rho because it is a constant value. So we do not plot it. It is not changing. So that's what I was looking for, the lower value. That was my submission. So all right, probably these are the answers which are correct, posted by Neerav as well as Deepak. Nice work done by them. 26, 14, 9.61, that is the turbulence intensity. And these are the value for kinetic energy, as well as you can calculate Reynolds shear stress. Right? So with this, I end my session. If you have still any doubt, we will be meeting tomorrow morning again for another session, and we'll discuss that.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
Thank you so much, Rajesh Jain sir. It was very nice session and very interactive session. I think all the participants have enjoyed and cleared their doubts
Yes,
also.
yes.
Yes. So now we are ending up this session too, and again we will meet at 4:15. So we are going to start our third session, last session of this day, at 4:15 p.m. Okay. So all of you are instructed to be on time so that we can start the session on time.
Okay, thank you, sir.
Yes, thank you.
Thank you, sir.